Now this recording will be on my computer, so I will post it later tonight under this week's module, as opposed to it being a cloud recording. I think I prefer doing it this way because there was issues with passcodes and things like that, and sometimes the passcode didn't match up with the recording. So what I will record will be available, and you won't need a passcode to see it. All right, so anybody can see it. Okay, so we'll get started. And anybody have any questions before we start? Okay. Now, don't be confused by what you see at the top here. It says chapter 16, and here it says chapter 14. I believe there was an earlier version of this textbook where this was chapter 16, and they didn't update the PowerPoints correctly. So, but this chapter here is chapter 14 in your textbook. So when I will post this, when I do post this in Canvas, it will say chapter 14. All right. So again, don't worry that it says chapter 16 on the top here. It has something to do with the way I saved it on my computer. It won't say that when it's actually posted in Canvas. All right. So what we're going to do is we'll start off with some thought questions like we usually do. And we're going to be talking about two types of probability, two different ways of looking at probability. And these are questions that sort of bring these up. It says here, if you flip a coin and do it fairly, what is the probability that it will land heads up? And so what do you think the answer to that is? Just flipping a coin once? No one? Well, it's 1/2, right? Because there's only two possibilities. There's heads or tails. So it should be a 1/2 chance that it comes up heads. But if we ask a question like, what's the probability that you will eventually own a home? Well, this is not something that we can just, come up with right away, right? We can't, it's not like flipping a coin where you can come up with a probability. This is something where you have to gather some statistics and come up with that answer. So if you were going to just guess at it, that would be another type of probability, right? If you're just guessing at, in terms of what's the probability of some individual eventually owning a home, maybe in the next 5 years, more of a guess from those people. There's another one. Explain what it means for someone to say that the probability of his or her of all right, the English is not great here, but what's the probability that someone will eventually own a home is 70%. Can somebody tell me what that means? Where we're going to say, let's select somebody at random. What's the probability that they're eventually going to eventually own a home? Let's assume that they don't. Is 70%. So what does that mean? Can anybody explain what the 70% represents? Can everybody hear me? You can hear me? Okay, I just want to make sure I'm just not talking to myself. Well, what it means basically is if you, two things. If we select somebody at random, there's a 70% chance that that person will eventually own a home in the future. That's the number one interpretation. Okay. Second interpretation is that that this probability estimates the proportion of the entire population. Let's say a younger population who will eventually own a home. That's what it means. 70% means about 70% of young people will eventually own a home. So it can be looked at as an individual probability. Select somebody at random, what's the probability that they will eventually own a home, or a proportion of the population. that owns a home. All right, now let's look at this question. This is my previous class. We had a little bit of a debate about this. Suppose somebody says this: the probability that I will eventually own a home or any other particular event happening is 1/2, because either it will happen or it won't. So my question to you is, what's wrong with this way this person's saying? You know, you can picture somebody saying this, right? Well, it's got to be 1/2, because either the person's going to own a home or they're not. So what's wrong with this statement? Anybody?
Just because there's two different options doesn't mean one is like they're both equally likely. You know, one could still be more likely than the other.
That's right. That's right. So let me give you a good example. Just one. Suppose you had a 6-sided die, right? And you wanted to know the probability that you would roll a 1. Well, there's 6 possibilities. So what is the probability of rolling a 1 if there's 6 possibilities? Anybody? Well, the probability of rolling a 1 as opposed to a 2, 3, 4, 5, or 6 is 1 out of 6. The probability of not rolling a die, rolling a 1 with your die, is 5 out of 6, because there's 5 other possibilities. So there are 2 outcomes, right, that are opposite each other, rolling a 1 and not rolling a 1, and they're unequal probabilities. So you're absolutely right. Julie, right? Julie's the one who mentioned that. Yes. So it doesn't have to be 1/2. Most people look at probability that way, don't they? They see either or and they think it's 1/2. But one of the things that you'll learn in this course, this course doesn't really develop probability as much as a regular Stat 1 course does, but at least it gives you this idea that probabilities are not necessarily equally likely. All right, there may be some unequal probabilities, but there are certain rules that we will follow when we calculate probability. All right. Here's another question. Why do you think insurance companies charge young men more than they do older men for automobile insurance, but charge the older men more, I guess, than younger men for life insurance? I'll give you a chance to think about that for a second. The answer, hint, has to do with probability.
Based on the probability that like they're more likely to use it, I guess, like younger men would probably be more likely to be driving.
More likely to be driving. Okay. I think I drive as often as I did when I was younger, but that's an interesting proposition. Anybody else?
Young people are more likely to get into a car accident.
Yeah. Because think about what insurance is for, right? It's to protect against negative events like a car accident. So younger men, we're talking about really young men, are more likely than older men, not really old men, but older men, to be in an accident. And that's why they get charged more. Exactly right. How about the reverse for life insurance? This one you have to think about a little bit. Life insurance means when you die, money goes to a beneficiary, somebody else, maybe a large sum like $100,000 or $500,000. Well, with life insurance, as opposed to automobile insurance, life insurance is based on life expectancy. How many years are you going to be alive? And an older person, more likely, is going to be alive for a shorter time than for a younger person, more likely. Yeah. So what does that mean? That means that it's going to be sooner rather than later that the life insurance company has to pay a claim for that person dying, for an older man than for a younger man. And that's why they charge more. They're going to charge more because they have to, there's going to be sooner, more likely that they're going to have to pay out that large sum of money. All right, so that was a little interest. That was pretty interesting. All right, let's look at another thought question, which is what we're going to deal with towards the end of today's session, practical application of learning probability. How much would you be willing to pay for a ticket to a contest, in which there was a 1% chance that you would win $500 and a 99% chance that you would win nothing? So what we're really asking for is, what's the maximum that you would pay to participate in this game? So what do you think? And the previous class had about 3 or 4 different answers for this. Interesting answers, actually. Okay, so don't be shy. You don't even have to say your name, because I don't see everybody's face at the currently. So you could just yell out what you think the answer would be. No one has any idea what you'd be willing to pay?
The most I'd be willing to pay is $4.99.
Okay. You are a stickler. Why $4.99?
Because if it's $5, it's like breaking even. And
Right.
anything more than $5, it's a net negative.
Right. How did you come up with the $5?
It's just out of 100%. So it's $500 times 5.
Okay, good. So what we're going to learn is a little calculation a little bit later, where we're going to find what's called the expected gain or loss. All right, expected. Expected means what we would earn over the long term if we repeated this game over and over again. So the expected gain here, by the way, is 1%, which is 0.01 times 500. But we can't forget about the other part. The other part is if you lose the game, okay? If you lose the game, in this particular case, you win nothing, and there's nothing in this scenario that says anything about cost of participation, right? You don't have to pay anything for it, which is unusual, but so 0 happens to be the net, the gain or loss if you don't win, and there's a 99% chance of that. So you have to multiply the probability times the amount for each case, each outcome, and then add up those products and you get your answer. So in this case, it's 0.01, which is 1%, times 500, plus 0.99, 99%, times 0, which is 0. All right, so $5 plus 0 is $5. That's the expected gain. So you're right, $4.99 is the most that you can gain. So very, very clever answer. I like it. What does the word probability mean? Well, there's 2, in this book at least, there is 2 interpretations. If you've taken statistics before, they would talk about 3 interpretations, but we're just going to talk about these 2. One type is one where we can run an experiment, basically, and repeat the experiment over and over again and come up with a probability that way. Or you can just assess based on your own personal beliefs. So there's a personal beliefs outcome or interpretation. The first one's called a relative frequency interpretation. This is the one where you can run an experiment over and over again. And then the second one that's mentioned here is personal beliefs. Basically, you're sort of guessing. So what is this relative frequency interpretation? What does that mean? Again, it applies to situations that can be repeated over and over again. And, let's say you repeat an experiment 1,000 times. Let's say you're counting the number of heads in 1,000 flips of a coin, and you want to count the number of heads. Well, the relative frequency is related to this idea of counting. You're counting the number of heads in 1,000 flips of the coin, and that's your numerator of this of a fraction, and the denominator is going to be the number of times you flip the coin. So if you flip a coin 1,000 times and you get 490 heads, then the relative frequency probability would be 490 divided by 1,000, or 0.49. All right. Now, sometimes you are able to know the probability of one case where you just run the experiment once, such as flipping a coin or rolling a die. You know the probability ahead of time, and sometimes you don't. Sometimes you have to run the experiment. For example, item number 2 here says commuting the work daily and observing whether a certain traffic light is red when we encounter it. Well, we don't know ahead of time the percentage of people who observe a red traffic light at that particular signal when they reach that intersection. We don't know, so we have to run the experiment. So sometimes we know ahead of time what the probability should be, and sometimes we don't. But the important point is, with the relative frequency approach, we run an experiment over and over again to come up with an answer. All right, and here's the whole idea. This is why it works. It's called the long run relative frequency. And what it means is that the more times that you repeat an experiment, more times that you repeat it, the closer the relative frequency is to the actual probability, to the actual proportion of time that it occurs in the long run. Okay. For example, and again, this book is kind of old, so, but suppose in terms of babies being born, we just think about males and females, not any other choices. Just think about males and females. So we think of 2 choices, and suppose the long-term relative frequency of males born in the US, and look how old this is. It's very old, right? Almost 30 years old, is 0.512, right? Now, if that is the relative frequency of males, what must be the relative frequency of females? Anybody have an idea? Well, it would be 1 minus this, and I'll get to that in a minute, would be 0.488. All right. Okay, anyway. Suppose we were watching babies being born, and suppose we were watching for 1 week, 4 weeks, 12 weeks, all the way up to the whole year. And we counted the number of boys for all the babies that were being born, and we took a proportion or percentage. What we would come up with is something that might look like this. It doesn't have to, of course. There will be some variation. But the important point is that the longer the number of repetitions that we have, or the more the number of repetitions that we have, the closer the proportion will end up being to the actual long-term probability or proportion. If the answer is 0.512, and notice that the numbers are getting close to that as we increase the number of repetitions, number of weeks in this case here, the proportion of boys is getting closer to that 0.512. All right. So this is why we use probability in statistics, is because of this idea of long-term relative frequency getting close to the actual probability, the actual proportion of the population that has that particular characteristic. Okay. All right. Any questions about that? Because that's an important idea. That's why insurance works, by the way, because they use long-term proportions, especially the life insurance industry. All right, determining the probability of an outcome. All right. Well, sometimes, again, we know it up front, such as flipping a coin. If we assume that when we flip a coin, it's a fair coin, which means it's equally likely that we would get heads or tails, then we would say the probability of getting heads is 1/2. The probability of tails is 1/2. Or if we don't know that ahead of time, we run a relative frequency experiment. Okay. And then we come up with our probability. Both of these would be considered to be under the overall heading of a relative frequency interpretation. Okay, because in both cases, either we know it up front because of the nature of the experiment, or we run the experiment over and over again. So what are the characteristics of a relative frequency interpretation of probability? Well, it can be used or applied when situations can be repeated numerous times, and we can observe an outcome each time. Makes sense, right? Number two, the relative frequency settles down to a constant value or close to a constant value over time, over the long run. We saw that with the idea of the probability of a boy, right? Number three, this type of approach does not apply to situations where the outcome one time is influenced by or influences the outcome the very next time. In other words, if we run an experiment, we don't want a situation where one repetition of the experiment influences the next repetition of the experiment. In other words, if we flip a coin, we don't want that outcome to influence the next result of flipping the coin. I mean, an example would be, let's say, you flip the coin 1,000 times, maybe your arm starts getting tired, right? So the outcome of the previous outcome does influence the next one because your arm is getting tired and you're having trouble flipping it fairly. So we do want, in general, when we use this relative frequency approach, we want the outcomes to be independent of one another. You'll see this word used a little bit later, independent of one another. The personal probability interpretation just means that we just, we have a sense or idea, maybe based on our own experience, of what the probability would be. That's all. It's basically what you believe will happen. Now, probabilities in general have to be between 0 and 1, whether it's a relative frequency interpretation or a personal probability interpretation. It has to be between 0 and 1. Now, they use the word coherent here. They do define it in the book. It just means that your personal probability doesn't contradict, one event doesn't contradict the personal probability of another event. Another has to be consistent. I guess consistent is probably another word they can use here. But all probabilities, no matter how you calculate it, has to be between 0 and 1. Now, what's a probability of 0? Can anybody tell me what a probability of 0 would represent?
There's absolutely no chance that it happens.
Absolutely no chance it happens. That's right. It's impossible. How about a probability of 1? What does that mean? It's
going to happen every single time. It's 100%.
Yes, that's right. Exactly right. It's absolutely certain to happen. All right. So let's move on. Now, we're going to start looking at rules of probability. Now, again, if I was teaching a course, a standard course in statistics and probability, I would go into more detail than what they go into here. But this is the level that they want to teach this course at. So this is fine. You'll learn enough to get a feeling for probability. It says here if there are only 2 possible outcomes in an uncertain situation, then their probabilities must add up to 1. Let's think about that. Let's think about this idea again of a boy or girl being born. Let's assume again just 2 possibilities, boy or girl. And let's say the probability of a boy is 0.51. What is the probability of a girl? Well, let's assume those are the only 2 possibilities, boy or girl. So if the probability of a boy is 0.51, and those 2 probabilities have to add up to 1, which means certainty, right? It's either a boy or a girl. Then the probability of a girl has to be 1 minus 0.51, which is 0.49. So that's how you figure out the other probability. There's only 2 choices, and you know the probability of one of them, you know the probability of the other. Another example again is when we roll a die and there's 6 choices. So what's the probability of rolling a 1? Well, we know that's 1 out of 6. What's the probability of not rolling a 1? Well, that's the other possibility, right? There's only 2 choices in that case. You either roll a 1 or you don't roll a 1. Well, rolling a 1 is 1 out of 6. Rolling anything other than the 1 has to be 5 out of 6, because the sum of those equal to 1. All right, certainty, right? Everybody clear on the rule number 1, how it works? All right, let's look at rule number 2. If two outcomes cannot happen simultaneously, they are said to be mutually exclusive. Mutually exclusive. Okay. Now, what does that mean? Well, let's go back to the previous case here. If we only have 2 outcomes, we have a boy or we have a girl, all right? And we assume that a child cannot be both, then they are considered to be mutually exclusive. And if they are mutually exclusive, then if we ask what is the probability of one or the other outcome happening, it is equal to the sum of their individual probabilities. They have to be mutually exclusive for us to add the 2. All right? Now notice the word or here. We use the word or, it means to add the probabilities. What's the probability of, what's the probability of, let's do this example, example 5. All right. If you think probability of getting an A in your statistics class is 50% and the probability of getting a B is 30%, now you know they have to be mutually exclusive events, right? You're not going to get both an A and a B in this class. You're going to get either an A or a B. So what's the probability of getting an A or a B? It's the sum of those 2 probabilities, which is 80% or 0.8. And most of the time when we ask for probabilities, we want them expressed as decimals, but if you want, you can also express it as a percentage. Now, notice that the 2 probabilities don't add up to 1. That means there are other possibilities, right? And of course, you can have lower grades and a B, right? And that's a C or less. Well, what is the probability of getting a C or less? It's got to be 100% minus 80%. Because again, getting a C or less is mutually exclusive from the probability of getting an A or a B. So it has to be 20%, which is 100% minus 80%. So we're not, so in this sense, we're combining rules number 1 and number 2, right? Rule number 1 says, well, rule number 2 says, the sum of getting an A and or a B is 80. And then using rule number 1, the chance of getting a C or less is 100% minus 80%, which is 20%. All right, so that's mutually exclusive. Now you cannot confuse this with the other rule, which says if 2 events do not influence each other, and if knowledge about one doesn't help with the knowledge of the probability of the other, the events are said to be independent of one another or of each other. Now, 2 events can be independent and not be mutually. They can be either mutually exclusive or not mutually exclusive. These 2 terms are not connected with each other. All right. So, but anyway. Now, independence. Let me give you an example of a silly example of 2 events that are independent. Suppose you wake up in the morning, look out the window, see that it's full sunshine, and you think, all right, what's the probability that it will rain? You think, oh, this is of course your personal guess, and you say, all right, I think it's about 10%. I can't say 0 because, you know, in some days it's nice in the morning and then it rains in the afternoon. So you'll say 10% chance. And then you see something else happen. Some person's walking their dog, right? So that's another observation. Now, do you think the observation of the person walking the dog has influenced the probability of it raining? And the answer is probably no, unless the person has put a raincoat on their dog. The two events don't relate to each other. The idea of a person walking their dog should not change your idea of your idea of what the chances of it raining later in the day. So the chances remain 10%. So those two events are independent of one another. They don't influence one another. All right. And in this course, we're only going to be dealing with independent events. We're not dealing with dependent events. So let's look at an example. Suppose a woman will have 2 children. They're planning on having 2 children. Assume whatever the outcome of the second birth is independent of the outcome of the first birth. In other words, this lady's not trying to influence the gender of the child in some sort of genetic procedure or something, assuming that it even exists. All right. And assume that the probability of a boy is 0.51, which means the probability of a girl is 0.49. You may ask, what if we just randomly select a lady who wants to have 2 children? What's the probability that the first child is a boy and the second child is a girl? Well, if they're independent events, then we simply multiply their individual probabilities. That's what we're doing here. So if the question is, what's the probability if the first child is a boy and the second child is a girl? Notice I used the word and, A-N-D. Then we multiply the probabilities. Remember, with mutually exclusive events, we mentioned that before, we use the word or, and we add probabilities. With independent events, we use the word and we multiply probabilities. Okay, you see the difference? If I was going to say something like, I'm going to roll a die twice. And what's the probability that I get a 1 on the first roll of the die and not a 1 on the second roll of the die? Notice I would use the word and. Well, if I get a 1 on the first roll of the die, that's 1 out of 6 is my probability. And the second roll, which is independent of the first roll, I don't get a 1, it's 5 over 6 is the probability. And I multiply those two fractions. 1 out of 6 divided by 5 divided by 6, which is 5 divided by 36 if you multiply those two probabilities. And you can do that because I use the word and the two outcomes are independent of one another. An example of mutually exclusive would be, I roll a die once. What's the probability that I get a 1 or a 6? See, I used the word or, right? A 1 or a 6. Well, the probability of getting a 1 is 1 out of 6. The probability of getting a 6 is 1 out of 6. So I add those two probabilities. They're mutually exclusive, right? If I'm only rolling the die once, and I get 2 out of 6, or 1/3. That's the answer. All right. So you see the difference between those two? Mutually exclusive and independent. Mutually exclusive, you're going to add. Independent, you're going to multiply. Any questions about that? Okay. Guys are unusually quiet today. All right. And here's rule number 4. Rule number 4 says, this one needs a little bit of an explanation. If the ways in which one event can occur are a subset of those in which another event can occur, and the probability of the subset event cannot be higher or greater than the probability of the one from which, let's just say from which, it is a subset. That's a pretty complicated way of saying this. So let me explain this, all right? Through example 10 is a good example. All right, suppose you're 18 years old and speculating about your future. Excuse me. You decide that the probability that you will eventually get married and have children is 75%. All right, so this is some personal belief probability. So logically from this, by using this rule number 4, your probability of getting married must be at least 75%. Now, can somebody explain why?
Because for you to get married and have children, it has to be like you have to get married. So
That's right.
it leads to at least be 75% because you got married and you had kids. You can't get married and have kids without getting married.
All right. You're absolutely correct.
Thank you.
What is, you're welcome. What is the bigger set in this case here? That, you know, the small set, the subset is married and having children. What is the bigger set?
Do you mean like what is the entire sample size? Like everything you could possibly do in your life, like get married or not get married or have
No,
kids
no,
or not
no,
have kids?
no. You don't want to get that diversified. What is the bigger set, the biggest, bigger set than that, if you're getting married? Sort of,
Whether you have kids or not have kids.
right. The set here is people getting married, and you just hit on it. People getting married either have children or don't. If you're married and have children, that is a subset of all the people who get married, because people who get married include those who don't have children. See what I'm saying? So that is a bigger set, and therefore the probability of selecting from the bigger set has to be at least 75%, because it includes people who get married and don't have children. Does that make sense? Picture a big circle where you just stuff in there people who get married. And then you say, all right, everybody who gets married, who have children, go to the left side of the circle. It's the left half of the circle. And everybody who gets married and don't have children, go to the right side of the circle. All right. And you see what I'm saying? And so if 75% get married and have children, then that's the probability. There's more people inside that big circle of just people getting married, because there's people in there who are on the left side. There are people who don't have children. All right. Can you picture that? So there's more people who get married than people who get married and have children. So therefore, the probability, if the probability of getting married and having children is 75%, the probability of just getting married without knowing whether they have children or not has to be at least as large as 75%, because it's just a bigger group of people. Yeah. So that's where they're sort of coming from here. And you're absolutely right, James. You were talking about how about people don't get married. Yeah, that's, you know, if we throw in everybody, that's even a bigger group, right? So you could even logically say, yeah, those people have to even be bigger than the people who just get married, right? People who anybody, whether they're married or not, is even a bigger group than people who get married. That probability has to be even bigger. So that's good. Anybody have any questions about that? Does that sort of make sense to you? I hope. Again, you guys are very quiet today. All right. Now this slide here is for the more mathematically inclined, but I'm going to go through it anyway and we'll look at an example, because what they're trying to do here is derive a formula that you can use for problems like the one they're about to do. But I'm going to show you that you don't need the formula, all right, if you're not mathematically inclined. So they're trying to sort of use symbols here. And if you like algebra, this will hopefully make sense to you. Suppose the probability of a certain outcome is P. Remember, P has to be between 0 and 1. Therefore, the probability that that outcome will not occur is 1 minus p. All right? Because the probability that it will occur plus the probability that it will not occur is certain. It's a certain thing, right? It's either going to occur or not going to occur. That is certain, and that's equal to 1. Suppose we make the assumption that each of these outcomes are independent of one another. All right, so we can use that multiplication rule that we talked about earlier. That was the rule number 3, I believe. Now, suppose we were interested in the following. Suppose we were going to repeat an experiment multiple times, and we want to know what is the probability of getting to the outcome. In other words, maybe we don't get the outcome, and then we get the outcome. We want to know what's the probability of getting the outcome. Well, let's say we repeat the experiment. Let's say we get the outcome to occur the very first time we do the experiment. Well, obviously, the probability of that occurring is p, right? That's the probability of the outcome occurring. If it just took one roll of the die and we got our 1, well, the probability is 1 out of 6. Okay, makes sense? Suppose it took 2 repetitions of the experiment to get the outcome. In other words, the first time we did the experiment, we did not get the outcome, but the second time we did. Well, the probability of that happening is 1 minus p, of not getting the outcome on the first try, times the probability of getting the outcome on the second try. Again, if we, using the example of rolling the die and getting a 1, the probability of not getting the 1 on the first try is 5 out of 6. And the probability of getting a 1 on the second try is 1 out of 6. So 5 out of 6 times 1 out of 6 is 5 divided by 36. Suppose it took 3 tries for us to get the outcome. In other words, in the first 2 tries, we did not get the outcome. That's the 1 minus p here, multiplied twice. And then we got the outcome on the third try. So it's 1 minus p times 1 minus p times p. 1 minus p times 1 minus p is 1 minus p squared. That's 1 minus p squared times p. And then you can see this continuing. You know, it took 4 outcomes to get 4 repetitions of the experiment to get the outcome. So the first 3 are not the outcome, and the fourth one is. Notice it's 1 minus p cubed times p. All right, so you can see the sort of hopefully see a pattern here. Again, if you're math oriented. All right. So let's just look at an example of how we might use this as an example. Suppose the probabilities have to do with having a boy or a girl. You know, suppose you're trying for a girl. All right, so you're going to keep trying until you have a girl. So this family here, this couple here, got it on the first try. So the probability of getting the girl is 0.49. This family here took them 2 children. The first was a boy. They tried again. They had a girl. What's the probability of that event happening? It's 0.2499, which is the product of 0.51, having a boy in the first try, times 0.49, having a girl on the second try. What if it took 3 births before you had your girl? You had 2 boys first, and then you had your girl. Well, you multiply these 3 numbers, you get 0.1274 is that probability. What if it took 5? Maybe people would give up by this time, right? But maybe this couple didn't give up, and it took them 5 children before they got their first girl. 4 boys, and then the girl. So what's the probability of that? That's a little over 3%. And then maybe another couple, they were very ambitious, and they kept going until they got to their 7th baby. They had 6 boys, and then they finally got their girl. And the probability of that is less than 1%, it's 0.0086. So this is sort of the type of scenario they're describing here. And they said you could do it this way, or you can use this formula, all right? Use the formula. So if you're into formulas, you can try it. If you don't like formulas, just use this type of way of doing it. All right. So, for example, here, if it took two, well, let's say this has to do with interacting with somebody with AIDS. All right. Let's say HIV. Right? So again, this is an older book, so this was on people's minds a lot back then in the 90s and early 2000s. Suppose probability of infection is 1 out of 500, all right, which is 0.002. That means the probability of not being infected. This is just having an encounter with somebody who has HIV is 0.998. So the probability of being infected by the second encounter, okay, is going to be, you're not infected on the first 2 encounters, on the second encounter, not being infected on the first encounter, but being infected on the second one. It's going to be 1 minus 0.002 squared. Now, if you're not into this sort of thing, this may be confusing to you. You might like, oh my God, I can't do that. All right, that's okay. Because you could do it this way. You could say, all right, probability of not being infected is 0.998. My first encounter, I was not infected, but I was infected on the second encounter. So 0.998, the probability of not being infected, times the probability that you are infected on the second try. And you multiply those 2 numbers and you get 0.001996. I'm sorry. What do they do here? Cumulative probability. Okay. Well, that's the problem. That's your answer here. Okay. Now, here they're saying, what's the probability of infection by the second encounter, not with 2 encounters? So they say by the second encounter. That includes encounter number 1, where you get it on the first try, plus on the second try. So you have to add these. You have to add 0.002 plus this number to get 0.003996. All right. So this is a little confusing. I think if I was going to ask you a question like this, I would probably hold your hand, so to speak, and try to get an answer from this type of table here. So don't worry about this so much if you read it. Again, it's for those people who are more math oriented. Now this part here, I do want you to know, I do want you to spend some time on. So we're going to spend the next, I would say, 15 minutes so on this. Okay, and make sure, hold on one second. Make sure the person just came in. I think this person is part of her class. Yeah. Okay. All right. This has to do, this is a practical application of probability. All right. So this concern yourself with a little bit more. We did something like this with that game of chance before we talked about. And we talked about insurance also. So let's look at this particular insurance situation. All right. It says all customers are charged $500 per year. All right. So they pay $500 per year. It's called a premium. They pay it to the insurance company. Suppose that only 10% of people overall will file a claim for whatever this insurance is for. We could say health insurance, accident insurance, whatever it is. And 90%, that means 90% of people don't submit a claim. Suppose that in this simple situation, whenever a claim is submitted, the company pays $1,500. All right, it just automatically pays it. All right. So the question is, what is the average gain per customer for this insurance company over the long term? How much are they making? Now, it's obviously if they're not making any money per customer, they're going to be out of business, right? They're not going to last very long. So how do we do this? Well, This is from the perspective of the insurance company's perspective, all right? How much are they expected to earn per customer? Well, they're receiving $500 per year. That's revenue coming into the company. Anytime they pay a claim or have a claim, they're going to pay $1,500. That's money going out of the company. So $500 coming in, $1,500 coming out. However, the probability of a claim is 10%. Probability of not having a claim is 90%. So we have to consider the overall net gain to the company in both of these situations. Either there is going to be a claim and the claim is paid, or there's no claim and that's it. There's nothing being paid. So is the claim paid? We look at yes, or in a sense, claim is filed and it's going to be paid. What's the probability of the claim? The probability of the claim is 10%, 0.1. Now, it's very important in this type of case that you convert the percentage to a decimal. Do not multiply a percentage, a whole number. You multiply the decimal, the proportion, okay? So you write it down as a proportion, 10.10. What is the amount gained if they pay a claim? Well, it says negative 1,000 here. Can anybody explain why it says negative 1,000?
Because they have to pay out money instead of getting money. Because
But how much are they paying out?
$1,000, like if they got approved
No,
for,
they're not paying
if
out
they're-
1,000. How much are they paying out if they have a claim?
well, they're losing 1,000.
Well, yeah, but they're paying the customer $1,500.
Oh,
Yeah,
yeah,
you're
'cause-
right. You're right. Money's coming out, right? I think that's what you mean, right? Money's coming out of the company. But they're paying. They're not really losing money. This is a contract. They're paying what they're supposed to pay. They're paying $1,500. But that customer paid them $500. So money coming in is a positive number. Money going out is a negative number. 500 minus 1,500 is negative 1,000. That's where they came up with the negative 1,000. All right. So that's their net gain. It's actually a net loss, right? It's a net loss of $1,000. Now, if no claim is paid by a customer, that's a 90% chance of that happening. And how much is gained? Well, they got $500 premium from them. That's plus $500 coming into the company. So what is the average gain? The average gain over the long term per customer? Well, it's simply the probability times the amount gained for each scenario. The two scenarios in this case here are either a claim is paid or it's not. And when it's not, there's a 90% chance of that happening. $500 was taken in by the company as a premium from the customer. In the case of paying a claim, well, $500 came in, but they had to pay $500 going out. That means there was a net loss of $1,000. That's where they have a negative here, by the way. The negative should be really inside the parentheses here if you want to be precise. I'll put a plus here, but you could put the negative in front if you want, right? This might be confusing to a new student, right? Because you think, oh, when we do this, we put a negative in between these two terms. No, it's positive. It just happens this negative should be inside the parentheses, and it should say positive 0.10 times negative 1,000. But they're taking the liberty of moving that negative sign out to the front. Okay, and that's why it says negative here. When we do this problem, we always do put plus. We always add the products. Okay, we don't subtract the products. So just know that the negative is here because it literally should be inside the parentheses. Regardless, it comes out to the same answer as $350 plus. So the company is making $350 per customer. Okay, that's the net gain long term. That's the expected gain per customer. If they had 1,000 customers, the overall expected gain would be $350,000. That's how much before, let's say before a year starts, that's how much you would expect to earn from these customers, 350,000 for 1,000 customers. Okay, so is that clear how this works? We multiply the probability times the amount gained, and then we add the products, and we get our average gain. No questions? Again, for those who like formulas, we take what we do to find the expected value or expected gain or loss, whatever it might be. We take each of the values and multiply them by their respective probabilities. There might be more than two. There could be multiple of these. Here, they're saying there are K possible scenarios in this case. All right, for those of you who are math oriented, you can see that. All right, so these are the possible amounts to be paid out, and these are the probabilities. So we have to take each amount and multiply it by its probability, and then add up all those products, and we get our expected value. Okay, and notice here, they did put the negative sign inside the parentheses next to 1,000 because this is the net gain. It's a negative number, right? They didn't put it out here. They didn't put it, here. They put it inside the parentheses, and they put a plus sign in between the products. All right. So make sure you're adding, but the negatives here, just use your calculator. 0.10 times negative 1,000 plus 0.90 times 500. Hit enter. You'll get $350. That's your answer. And that's the expected value over the long term per customer. It doesn't necessarily, this is important here, doesn't necessarily represent one particular person or one occasion. Okay. It's an overall average. Okay. Over a large number of customers, $350 on average. You're gonna earn per customer. That's from the perspective of the company. Now, overall, what is the overall over the long term? Let's say a customer stays with this company many, many, many years. What's the overall average expected amount for the customer in this transaction? How much are they expected to gain or lose over the long term per year? It's not as hard as you think. If the company's expecting to earn $350 per customer, how much is over the long term, how much is the customer expected to lose every year? On average, $350. The two are a wash, right? When you add them together, it's zero. Now, companies typically, they pad their premiums. They put some additional money in there so they can make more money, all right? But in reality, this is like a casino, right? If a casino is making a certain dollar amount per person, that should be the dollar amount over the long term that a person in the casino loses. It should be, it has to be. Where's the money coming from? It's coming from the customer. The same thing here. This $350 is coming from somewhere. It's coming from that premium that the customer is paying. See what I'm saying? They're paying $500, $350 of that over the long term is going to who? It's going to the company. So they're losing $350, right? Out of the $500 that they pay, they're losing. Okay. All right. Anyway. And here's another case of a game of chance, right? Some lotto or something, California lotto, $1 that you pay for this thing. There's different prizes. There's 4 prizes. And there's for most people, they don't get anything, right? They lose. So, but it's only $1. So if you win $5,000, Your net gain is 4,999 because you paid $1. All right. If you win 550, your net gain's 49. If you win 5, your net gain's 4. This case here, you get a free ticket, so you don't lose any money. All right. The net gain's 0. If you don't win, you'll lose $1. Okay, you'll lose your $1 that was the cost of playing. And then you have your probabilities. Here are all your probabilities. By the way, if you add up these probabilities, should add up to 1, which is certainty, right? You're either going to win the $5,000 prize, or you're going to win the $50 prize, you're going to win the $5 prize, you're going to get a free ticket, or you're going to lose. That's it. So if you add up all these probabilities, notice these probabilities that winning $5,000 is really low, right? 1 out of 28,561 in this particular game, right? 1 out of 595 to win $50, 1 out of 33 to win $5, 0.242 to win, or 24.2% chance of getting a free ticket. And what's your chance of losing? 72.6% in this game, which is actually not that bad, right? I mean, considering for a game. But what is for you as a participant in this game, what is your overall average gain or loss for the long term? It better be negative, because if it isn't, that means whoever set this game up is an idiot, because they're going to lose money, right? So participants overall lose money. Now, can a particular person win? Of course, there's going to be somebody who's going to win the $5,000, right? Somebody, right? Somebody's going to win $50, but the probabilities are low. So the answer is the expected it's a loss, right? Overall, every time they play, they expect to lose overall 35 cents every time. Okay. So, but that's not bad. For people who want to play this over and over again, it's not horrible. I've seen games which are much worse than this, right? Any questions about this? Got a couple more minutes. Let's look at this particular one here. So, a measurement taken over a large group of individuals, the expected value can be interpreted as the mean value per individual. Okay. Mean value per person, right? It says here, suppose 40% of people in the population smoke a pack of cigarettes a day. I think now it's probably a lot fewer, I hope. So let's say 20 cigarettes, and the remaining 60% don't smoke any cigarettes. What's the expected number of cigarettes smoked per day by one person? Again, 0.4 times 20 plus 0.6 times 0 is 8 cigarettes. So on average, 8 cigarettes are smoked per person per day. This doesn't deal with any particular person. It's just what we expect to measure on a person selected at random. All right. Birthday problem I will skip for a later time, and then the slide here for those who are mathematically oriented, like all of these symbols and everything. This explains all the rules that we went through today. All right. So the schedule does show that we're supposed to cover again 2 chapters next time, and we're only going to cover one of them because we're going to look at, for the first half of Wednesday, we're going to look at some problems in the back of chapter 14. All right, we'll go over those. And then we're going to go over chapter 16 only, the second half of Wednesday. And then chapter 17 we'll leave for next week. All right. So the quiz that's coming up on Monday, next Monday, we'll cover only 2 chapters, chapters 14 and 16, and not 17 as I had mentioned before. All right. Because I do believe that you need some time. We need some time to review problem solving for this chapter here. So and see different types of problems that we can come up with. Any questions? Any comments? I think there was a chat here. Somebody said something. Hey, let me see what the chat says. Oh, it's just James again. Mentioned that before. Okay, good. No questions? All right. So what I'm going to do is I'll shut off the recording. Stop the